Welcome to Module 8 in our series on artificial intelligence. This module presents a brief review of optimization for machine learning. Specifically, this module will teach us about mathematical optimization as a precursor for the next module on gradient descent. I want to begin with a question, specifically what is mathematical optimization and how does it relate to supervised machine learning? An optimization problem is one that asks us to systematically find system parameters that satisfy some practical constraints as well as maximize positive characteristics, for example efficiency, and minimize negative ones, for example cost. One prime example is the traveling salesman problem that I think many of us are familiar with, and it asks us how do we visit all the cities on the map while traveling the minimum distance and ultimately spending the least amount of money. In short, mathematical optimization asks us to find the best configuration of a system or the best solution to a problem. Now, like we've said already, this module addresses optimization. It's a topic that we've covered extensively in other lectures, and we can see these threads woven throughout the last 7 AI modules. Here, we emphasize the aspects of optimization most relevant to machine learning, as that's the focus of this series. As stated previously, mathematical optimization searches for system parameters that maximize desirable characteristics or attributes as well as minimize undesirable ones. For example, can we build a car with high reliability and high speed with low weight and low cost? Generally, the optimality of a given characteristic is dictated by an objective function or a cost function. In essence, optimization concerns maximization or minimization of a real, quantifiable function that compares actual system behavior to that which is desirable or ideal. Next, there are some terms or characteristics that I'd like to review before we jump into examples. The first is a comparison of continuous versus discrete optimization. A continuous optimization problem is one that uses continuous functions and parameters. Pretty self-explanatory. And as we would expect, a discrete problem is one that utilizes discrete functions and parameters. Now, discrete problems may be simpler to solve or seem simpler to solve because only a finite number of possible system configurations exist, unlike continuous problems that present an infinite number of possible solutions. However, discretization can introduce challenges, such as reduced precision or increased sensitivity to small parameter changes. I'd also like to compare constrained versus unconstrained optimization. A constrained problem places no restrictions on how an optimal solution is defined. This allows us to choose a true globally optimal solution. For example, how do we minimize grocery spending if there are no constraints on that problem? One solution is to simply not go shopping, right? That would spend no money and the output of our cost function would be 0. Or to extend that idea even further, right, we could take food from our fridge and sell it, and that would yield a negative output, even smaller output from our cost function. Now, this solution allows us to find a globally optimal solution, but ultimately ignores the practical constraints that dictate why we go grocery shopping in the first place. A constrained problem imposes equality and or inequality constraints on system parameters as well as states, and these define feasible and infeasible solution spaces. For a constrained problem, an optimal solution must be chosen from the feasible space, even if a lower cost or higher benefit alternative exists within the infeasible space. Next, I want to compare linear and nonlinear optimization problems. A linear optimization problem, as the name suggests, is defined by its linear or affine objective function as well as constraints. Now, these are many times represented by a function that looks like this. The objective function is equal to ax plus b. We call this the affine form. And typically, these linear optimization problems are easier to solve due to their simple or relatively simple topology and constant slope. To minimize an objective function like as shown here, one must simply increase the parameters with negative slopes and decrease the parameters with positive slopes. A nonlinear optimization problem involves nonlinear, again as the name suggests, nonlinear functions and constraints. Now, this type of problem does not follow the form above. It may include higher order polynomials, exponents, trigonometric functions, logarithms, etc. And generally, these problems are more challenging due to their complex topology and potential to present multiple local maxima or minima, making global optimization harder. Next, let's take a look at a general or generic form of an optimization problem, and we can divide this into two pieces, the first of which is the objective function we represent as f subscript obj. This defines the goals or objectives of an optimization, and we may apply minimization or maximization to the objective function depending on the structure of the problem. The second piece consists of the constraints g and h. Together, they define the feasible solution region, and they may take on one of two types, equality or inequality types. types. So here we see an objective function that we want to minimize. It's subject to certain equality constraints denoted by g. This k is the index of the equality constraint. It accepts the input variables x, and we have assumed here a number n subscript g of these equality constraints. Then we have the inequality constraints denoted by h, again an index. It accepts the variables contained within x, and we have a total of n subscript h inequality constraints. Now an unconstrained problem, right, would present none of these constraints here. So our use of the term general form here is not equivalent to the term standard form as used or described by many textbooks. The previous slide presents a generic form of an optimization problem, but the term standard form is specific to certain linear optimization problems where the objective function is a weighted sum of parameters, where we have these coefficients c multiplied by our input variables x. It should be a maximization problem with inequality constraints, as well as use the assumption that all of the input variables x are greater than 0. Now, there are numerous methods to solve optimization problems. Many depend on the continuous versus discrete or linear versus nonlinear nature of a problem. We have to understand the problem type before we can determine how to solve. For an unconstrained problem, one may simply calculate the critical or stationary points of an objective function. A critical point is an input to a function that yields a zero derivative, or again, stationary point. This makes sense as critical points may represent a minimum or maximum extrema value. It could also potentially represent an inflection or a saddle point. A first derivative defines the location of a critical point, while the second derivative indicates its type, right? It tells us whether the slope is increasing or decreasing. An increasing slope would indicate a minimum, and a decreasing slope would indicate a maximum. Next, let's take a look at an example of a linear optimization problem. The first thing we need to do is define our optimization problem. For this, we want to minimize an objective function with respect to x, and this function is defined as 1.25 times x1. This is merely an index, minus 2.5 times x2, again an index, minus 3. Now this problem is unbounded if we don't institute proper constraints, so we're going to define those here. x1 must be greater than or equal to 0, and x2 must be less than or equal to 1. The second step is to calculate the first order gradient, or to differentiate the objective function with respect to both x values. And that yields essentially their slopes, a positive slope for the first x value and a negative for the second. And like we said previously, since our goal here is to minimize the objective function, we will want to minimize x1 because it has a positive slope, and we'll want to maximize x2 because it has a negative slope. So we minimize x1, driving it down to 0, and we maximize x2, driving it up to 1, as defined here and here. We then present the result. Our optimal solution is 0 and 1, and we can plug that optimal value into the objective function to yield the minimum cost, which is negative 5.5. Next, let's take a look at an example of a quadratic type nonlinear optimization problem. So we're slightly stepping up the complexity. First, we need to again define our optimization problem. We want to minimize an objective function with respect to x, and this objective function is defined as 3x1 squared plus 2x1 plus 2x2 squared minus 2x2 plus 5. Next, we calculate the first order gradient of the objective function with respect to x, and we end up with these two expressions that we set equal to 0 because ultimately, right, we're looking for the critical or stationary point. Now, this objective function is separable, making the solution or the solving process easier. Now this right here is relatively easy to solve. We merely need to find the x1 and x2 values that satisfy the equality to 0. So we analyze the first derivative and calculate the critical or stationary point, which is 1/3 or negative 1/3 for x1 and positive 1/2 for x2. Finally, we analyze the eigenvalues of the second order derivative or second order differential Hessian matrix to confirm that's a minimum. Now I'm not going to talk about this too much, but to make a long story short, this Hessian matrix here is positive definite, and therefore we've confirmed that this optimal solution is a minimum. Next, we continue to step up the complexity. We take a look at a third order polynomial type nonlinear optimization problem. We begin by defining the optimization problem. We want to minimize this objective function here, which is defined as x1 cubed plus 3x1 squared, so on. I don't think I need to read this whole thing. We then calculate the first order gradient of the objective function with respect to x, and that yields two second order polynomials that we set equal to 0. Now the nice thing with this example is we can still use the quadratic formula to solve this. But as we move on to higher order polynomials, so let's say a fourth order polynomial that would yield a third order polynomial gradient, right, we wouldn't be able to apply the quadratic formula for those, and we don't have a higher order counterpart. We don't have a cubic formula that we can use to solve them. So, but for this example, we can analyze the first derivative and calculate multiple critical or stationary points using the quadratic formula. We have two quadratic equations we need to solve, and so that yields 4 permutations. Now, how do we determine that the fourth represents the minimum? Again, as we showed for the previous example, we analyze the eigenvalues of the second order derivative, the Hessian matrix, to confirm that it's a minimum. So the positive eigenvalues indicate that this is a minimum. Now, I'm not going to talk about this too much. If you're interested in how to solve a problem like the previous using MATLAB, you can pause the video and take a look at this code here. So finally, let's take a look at a more highly nonlinear optimization problem. This is the last example we'll introduce in this module. I say introduce because we're not going to solve it here. It will serve as the seed for the next lesson on the topic of gradient descent. So we begin by defining our optimization problem. Again, we want to minimize an objective function as shown here, but now we've added a highly nonlinear term, the natural log term, and that will essentially prevent us from using algebra or something like the quadratic formula in order to find the critical or stationary points. Now, the next thing we would do is calculate the first order gradients as shown here, but as we see, we don't really have a good way, at least not yet, for solving for x1, and this is essentially what we're going to tackle in the next module. So I do want to return to assigning a homework problem with every module. Like I've said previously, I'll post the solution to this assignment after we have 10 attempts or 10 responses in the comment section. So consider the objective function below in terms of two variables, x1 and x2. This is a third order polynomial type nonlinear problem, so we went over an example similar to this, and the objective function is 1/3 x1 cubed minus 3/2 x1 squared. Again, I don't think I need to read this whole thing. I ask you to calculate the gradient of the objective function with respect to both input variables. I want you to use that gradient to find the critical or stationary points for which the gradient equals 0, both components of the gradient equal 0, and then determine which critical point or critical points represent local minima. Now, I am aware, or we are aware, that this problem is unbounded, and as such, a global minima exists as x approaches negative infinity, but we're not looking for that solution. In summary, this module reviews mathematical optimization for linear, quadratic, and third-order polynomial type objective functions using critical point analysis. I invite you to watch the next module to see a solution to the last example problem we presented. This next module introduces the gradient descent method, demonstrating how we may solve more highly nonlinear optimization problems.